Thank you everyone for joining, and we really appreciate our folks from Europe that are joining, some on a holiday and certainly later in the evening for them. So we really appreciate that. And welcome to our event to really cover Westport's Vienna Motor Symposium paper with Scania, as well as the TNO research that was done utilizing or on our HPDI platform. So an opportunity to really deep dive into the technical pieces. So I'm glad everybody could make it today. Now I'd like to pass it over to Fabien. Fabien is our new Chief Technology Officer and Executive Vice President of Product Development. He's brand new. I guess he only joined, I think it was a month ago now. So this is our first opportunity to get to know him. He's going to kick us off today, and then he'll also participate in the Q&A at the end. So I will pass this over to Fabien.
Yeah, thank you, Ashley. Thank you, the whole team, for organizing this webinar. I think this is a great opportunity to bring everybody up to speed about the latest developments that we've been able to do on hydrogen HPDI, quite exciting technology. What we'll go through today is we'll start discussing some of the applications of the Westport HPDI hydrogen fuel system on demonstration truck. So it will be two parts. First part, Erik Olofsson from Scania, from the Redon group, who is Senior Manager for Combustion Systems, will be taking through some of the engine testing work that was done, and followed by David Mumford from Westport. David has been with Westport for a long time and has been instrumental in development of the HPDI system and now its application to hydrogen. And then after that, we'll go in through some more details and comparison presented by Xander Seykens from TNO, who is a research center in Eindhoven, or actually in Netherlands. And he will be going through more details on a very specific study that they have done comparing port-injected spark-ignited hydrogen combustion versus the HPDI hydrogen combustion. So I think through all this material, you will be able to realize the potential and I would say the superiority of the HPDI when running hydrogen. And after that, we'll finish by a Q&A and be happy to answer any questions that you have. So thank you very much. And I guess we hand it over to Erik.
Or is it you, David?
I can certainly take a part of that. Fabien, if you'd like, you could also cover this one. I'm quite comfortable either way.
Yeah. Maybe let me say a couple of words about that. I think what we have been seeing in the marketplace certainly is a growing interest of IC engine running on hydrogen. And I think starting on our side in 2019, we really started looking into what our technology could do for hydrogen combustion. And I think the regulators are starting to turn around. And, I think more recently, there's some great discussion in Europe about allowing, some minimal amount of carbon dioxide to be produced and still be considered zero emission vehicles. I think this is a very important development. I think it's very clear that fuel cell vehicles and battery electric vehicles, especially for larger vehicles, may not be financially sustainable going in the future. And I think the industry is noticing, and the industry is really increasing the interest and activities on the hydrogen combustion side of things. And I think there are technologists like Westport, supplying full fuel systems and developing technology for gaseous fuel that are actually ready with technologies like this to support the industry. So I think you'll see through the material that is presented today that this is a real opportunity and something that makes a lot of sense for the environment and for everyone involved for the future.
So why is the Redon Group and Scania interested in H2Is in general and the H2 HPDI system more specifically? I will start with a 2 to 3 minute background, orally presented only, just to explain why we are interested in H2Is. As you all know, every truck manufacturer struggles with the question, what will the energy system of the future look like? And how do you adapt and how do you do this quickly and swiftly and be agile in your way of working? Every OEM is struggling with this and no one knows what the future would look like. And we know there are only 2 energy carriers out there that can be used in a heavy-duty truck implementing very close to zero CO2 emissions, tank to wheel. And we all know them as electricity and hydrogen. And as an OEM, you can influence the tank to wheel CO2 emissions, but unfortunately, you are completely in the hands of other actors in the society regarding the implementation of the production and the distribution of the energy carriers we need to succeed in our ambition to reduce tank to wheel CO2 emissions. So in other words, energy carriers and infrastructure are controlled by energy companies, authorities, and governments. and lie more or less completely outside truck OEM's control. We can state, if you carry it to extremes, that we have as little insight as anyone else into how well developed the systems will be for mega charging or hydrogen refueling stations in the future. We have no guarantee of a sufficient expansion of a network of energy stations for any of the energy carriers that can realize almost zero CO2 tailpipe emissions. And nor do we know what the respective energy carriers will cost, to be honest. In addition to this, we also only have vague ideas about how the customer perception of electric or hydrogen trucks will be. The only thing we know for sure is the fact that the EU has finally launched the CO2 tailpipe emission levels that OEMs have to meet, which is 45% reduction by 2030 to begin with. It will end with 90% in 2040. So we have very tough and legitimate demands on us, but we don't know what the conditions for meeting them will look like. And at the same time, we all know there is no alternative. We have to meet this. Close or shutdown is preferable to paying the invoked fines that arise in the event of non-achieved CO2 reductions. Or we have to start selling the low CO2 emission vehicles at a loss to increase sales. And this is a problem for every OEM. And in light of this, it can seem like a big risk to bet on just one of these horses, electricity and hydrogen. Investing in the wrong concept, if you invest in only one of them, can have disastrous consequences. As an OEM, you risk standing there with the wrong product, and thus great difficulties in complying with the future CO2 legislation and customers' wishes. But this fact puts all OEMs in a difficult position, how to afford to bet on both of these energy carriers, electricity as well as hydrogen. And we should be aware of the fact that at the same time, we need to keep the traditional fossil ICE engine extremely competitive. So we have to spend a lot of money, and we have to do that in a smart way to mitigate risk. The BEV is, for very good reasons, TRATON's main route towards CO2 neutral transport. So the techno-economic question then becomes how to complement this well-chosen strategy with a path along the H2 strategy. That was a short background. So this possible risk diversification must be carried out at low cost in order not to jeopardize TRATON's main route to CO2 neutral road transport of heavy goods, that is the BEV. And this is where the H2 internal combustion engine fits in, as it facilitates very low development, investment, and production costs due to well-known and relatively mature and robust technology. It also facilitates the possibility to use existing production facilities. And it also has a relatively short time to market. So it's therefore a capital efficient way to use hydrogen. And it's a very capital efficient way to mitigate risk. So H2 ICE will consequently not cannibalize the resources allocated to BEV, and that is extremely important. And simultaneously, it will make TRATON prepared for a possible future scenario where hydrogen plays an important role in the heavy-duty road transport sector. So, looking at the CBE1 engine, that's the engine now serving in the Navistar truck. It will be serving in the MAN trucks. It is serving in the Scania truck. It will have an annual production of around 300,000 units in the future. The free fuels, we can see for the foreseeable future that the CBE1 should possibly be able to convert our diesel. Diesel will be with us for a long time, unfortunately. Methane and hydrogen. So that's the free fuels we will have to be able to convert or burn in the engine. So from that, it follows that commonality between diesel, methane, and hydrogen engines will therefore be important in the future, extremely important. And there are a number of driving forces for H2 community or society or economy or what you would like to call it. First of all, we do have the steel industry being responsible for 7% of the CO2 emissions worldwide. The only way for them to become CO2 neutral is to start to reduce the iron ore with hydrogen instead of coke, as it is made today. And in the north parts of Sweden right now, it's huge activities in this area, probably the most intensive activities in the whole world, producing fossil-free steel. So that's a business that will drive the green hydrogen. On top of that, we have the big oil. They know molecules, not electrons. And as the world becomes defossilized, they will turn into the production, probably, and transport of hydrogen and other e-fuels. And as the primary energy system becomes renewable, we have to rely on volatile energy resources. In Europe, it will be the wind. This will place enormous demands on the ability to store energy. And this is where compressed hydrogen comes into the picture as a way to store energy. Probably the only way to store the required amount of energy. This is a huge amount of energy. If the whole primary energy in Europe, in EU, will be renewable. If the wind is not blowing for 2 weeks in January, when the sun is producing zero in the central parts of Europe, we need huge possibilities to store energy, and that's where hydrogen comes into the picture. And we do also have the fertilizer industry. They are looking for Sweden now because we have green electricity. They need to produce green hydrogen to be able to produce ammonia. And I guess Europe is also in a good position for the hydrogen society, as we have a huge grid for natural gas, and that will be used for hydrogen. And that means that the end consumers of hydrogen in Europe cannot be very sensitive to purity, because there will be some natural gas in the system also, more or less. So being able to handle the fuels, applying the HPDI technology to the gaseous fuels, methane and hydrogen, all three engine versions, diesel, methane and hydrogen, will be exactly the same from an engine perspective. The only thing that it differs between these three engines is the injector. The after-treatment system will not be identical, but similar. Hydrogen has no carbon in the fuel, and therefore there is no soot in the exhaust stream, and that puts us in a more simple position. So we can use one engine platform to be able to handle all fuels, diesel, methane, and hydrogen. Identical platforms, the same pistons, the same cylinder head, the same external gas change system, the same crankcase ventilation, everything is the same. So we don't need the SI Otto platform any longer. We can exclude that. And of course, that's a lot of money to be saved. This is true fuel agnosticity. We talked about the different driving forces for an H2 economy. Will it happen? No one knows, but if you're not prepared, it's a huge risk. If it happens and you're not prepared, you will die. But why is the HPDI concept, what's make it unique? Why is it so competitive compared to other H2I's concepts? And according to Scania Traton's, or at least Scania's way of looking at it, this type of system runs according to the diesel principle, which makes it possible to deliver very high torque and power density, diesel-like or higher. Since there is no knock, no pre-ignition, the fuel is not present in the cylinder during the compression stroke. Very good efficiency, diesel-like or higher. Hydrogen is a little bit higher than diesel, and methane is just below diesel. And the reason why hydrogen is so efficient is what is called the expansion. That's something that's a separate issue, but it's a fact. We talked about extreme commonality for diesel, hydrogen, and methane from an engine and after-treatment perspective. We will be able to create very competitive transient characteristics and low-end torque, and we'll be able to create powerful make-heat strategies at cold start. And these two last bullets are linked to the fact there is no carbon in the fuel, there is no soot in the exhaust, and this opens up very many doors for low-end torque, drivability, and very powerful make-heat strategies and cold starts, which makes it much more simple to cope with Euro 7 and EPA 27. And finally, I think personally, and I think that goes for many of my colleagues at Scania, that the way to take care of the existing fossil diesel fleet in Europe in the beginning of in the 30s will be to retrofit them with a more simple kind of dual fuel system that will reduce the CO2 emissions from these engines with 50 to 60%. And that will also push for the hydrogen infrastructure.
Brilliant. I think that brings it over to me. Thank you so much, Eric. That was a great introduction, and hopefully I can use that to expand in a few points around the presentation we did in Vienna. So just to start us off, and it kind of encapsulates a lot of what Eric spoke about. There's a study out of the North American Council for Freight Efficiency, which really looked into this problem quite a bit. And clearly this was a US study, but at the same time, very topical to Europe as well. The wonder of trucking today is in long haul, about 70% of our heavy duty vehicle CO2 comes out of those vehicles. They're very difficult to transition. As you can see on the left, the study looked at multiple methods of decarbonizing transportation. And their study really pointed to the fact that in the short range or the short haul, the battery electrics and hybrids did very well on short haul, but fuel cells and hydrogen combustion engines would really focus well on the long haul side. That was where the optimal use they found was. Now, on the next few slides, I'll expand on that a bit further, but the takeaway on here is hydrogen combustion engines really still have a place to play in the world we're heading into, and particularly around this heavy duty sector. I'll give you a bit of an overview on the two technologies that are available or have been used primarily in both natural gas and hydrogen. And a number of you are probably very familiar with the natural gas spark ignited systems. They're using very similar approaches with the spark ignited systems that are now coming out, but they have taken a few steps forward, and I know Xander is going to speak a bit further on that. The really big takeaways here are the HPDI system itself, and I think it looks like the animation isn't running. That's okay. The big improvement with HPDI is that we're able to run the diesel cycle as opposed to the Otto cycle, which a typical spark igniter is on. And as most of you are probably well aware, for many, many years now, approximately the last 60, 70 years, the trucking industry has transitioned to purely diesel. Now, that was done for economy reasons, fuel efficiency. And what we've found is if you can run an engine on the diesel cycle, you have the best opportunity for improved fuel efficiency. So the HPDI system, to Eric's point, is really a method of using that same diesel cycle, the same piston, the same after treatment, all of those same attributes that really made the diesel work well with just a new injection system. So in our case, we've we adapt that engine to accept the HPDI injector, but we've kept the same piston, we've kept the same turbo, and the CBE1 in particular is one of the most advanced engines in the world. So it's already highly efficient. We're able to build on that. And what you'll notice is that the power, the torque, and the efficiency are already areas where we can actually exceed that base diesel engine. And a little further down in this presentation, we're going to hit on that because this engine has actually achieved 51.5% brake thermal efficiency. These are numbers that a few years ago we didn't even dare talk about for combustion engines, but really now they're part of our lexicon for how we deal with the latest engines. Give you a very quick background or overview of our fuel system. And as I noted, it's one that is designed to replace the diesel fuel injection system. We started out of the University of British Columbia about 30 years ago in Vancouver. And at the time, we really just wanted to make a more efficient natural gas engine. That was our starting point. And we were trying to deal with emissions. There was a perception that we could really make a difference in that area. And the heart of what we did started from the fuel injector. And you'll see a little bit more about that as we move forward. But basically, the fuel injection system we use, the injector itself is the core of it. And that injector has a small pilot needle and a large outer gas needle. The pilot needle is really there just for ignition purposes. As we started working on that, we realized we had to do more to get the fuel system to work properly. So we've got some fuel conditioning. You'll see a little bit of that. And at the bottom in the middle, you'll see a device we call our gas conditioning module. That's the only other device that we add on the engine of any note that really just ensures the fuel pressures are controlled. And then finally, we realized we needed fuel supply. So as we talk about LNG, the pump on the right in this picture is the system that enabled our gas system. And at this point, it's probably a good point to note that natural gas itself remains a pretty good way to decarbonize the industry. If you are able to use renewable gas, depending on the amount of renewables in it, you can reduce your well-to-wheel CO2 all the way to zero. So this still remains a great system. But the important one that we came down to was in all of these cases, we use the same base diesel engine. And then the second fact that's really come out over the last 4 or 5 years is that while it worked really well with natural gas, we're actually able to run other fuels. And this is where hydrogen became extremely interesting. So the following slides, we're really going to focus in on that hydrogen combustion and still using that base diesel cycle. Here's where we are today. And in this case, a generic truck. Hopefully one day we'll see one with a Scania logo running around. But on the left-hand side of this screen, what you'll see is a fuel rail, the HPDI injector, and that gas conditioning module I mentioned. And that's really what we put onto the base engine. We retain the common rail diesel pump. The control system, which you see referenced on the right here, is updated obviously to manage all of the engine, not the engine function, the fuel system function, and it still functions the same as the original diesel. To be very honest with you, many truck drivers can't actually tell they're running in an HPDI truck. We've been asked in the past if we could turn the gas on. It's simply very much like the original engine. Now, on the right-hand side, in this particular picture, you see the system as it is today. And in this case, that's with all of the LNG components, the LNG pump and the LNG tank. Now, as we go down, I'm going to highlight where we go with the hydrogen systems. Back to Scania's state-of-the-art engine, the 13-liter CBE1. We've been running on a number of engines, but the CBE1 is the most advanced engine that I'm aware of that we've run HPDI on currently. It's a very good diesel engine, and it's a good demonstration of how far the technology has pushed on the engine side. What we did was we took our base HPDI system. So the top area you see here is what we sell today for natural gas, and we simply put it straight onto this engine. There was a little bit of machining, a little bit of adaptation, but basically it's not a major set of work to fit this. And then we continued to run that engine for the last few months, but very few hours, relatively speaking. This is not a major development. And yet we've managed to achieve all of our goals quite quickly on it. And obviously, as we move forward, we'll look to do more than this. But we'll go through where we are on this engine now on the next few slides. I'm not going to beat around the bush. Let's go straight to the results. And on this slide, what you'll see is a quick map of the torque curve and down the what we would call at the 1200 RPM speed. You've got at the low loads 900 RPM. We're running on the torque curve with no issues at about 48% BTE, brake thermal efficiency. And that torque curve tends to run between about 46 and 48% right on the curve. So that's at our full load, full torque conditions. Now, as you move down the A speed, you'll see here that the brake thermal efficiency in the middle actually exceeds 51 or 50% in that range. So you'll see a 50.8 at about 50% load and 51.5% at about the 75% mode. We chose these points primarily to illustrate where the truck does have a fair bit of its running and where the important torque curve sits. A takeaway right away is that we're running about 28 bar BMEP. So on the order for a 13-liter engine, about 2,800 Newton meters, which is well up there with the top end of the 13-liter market right now. In addition to that, we're able to run NOx levels that we believe with the after-treatment tuning are correct. These are engine-out NOx levels, just to be clear. But with the after treatment, these would allow us to meet the Euro 7 targets that we're heading towards, which for anybody that's not familiar with the latest targets, is around 0.09 gram kilowatt hour. We are able to reduce these even further. So as we look toward the US market, for instance, that could be an option. We've got a couple of levers. Those include the system pressure, but also EGR if needed. We can pull NOx down even further. We've demonstrated quite easily down to 3 gram kilowatt hour. And in fact, we can get a little lower than that. And then last, that all important question around CO2. The pilot quantities that we use are quite small already for natural gas, but we have been looking at pushing them lower because hydrogen ignites so easily. So running on the order of 2 to 3 milligrams allow us to go toward near zero CO2 emissions. As you'll probably understand, there's a little bit more pilot relative to gas at lower load and nearly entirely gas as you go to high load. So we are able to currently to reach up to approximately 98% CO2 reduction on the upper end of the modes. I'll keep us moving. Let's head down. And this
David,
slide, sorry,
can
please go ahead,
make a
Eric.
short comment on the previous slide?
Absolutely, please do.
The torque curve you're showing here is the maximum torque curve we are running on diesel. So it's the same as the maximum torque curve achieved on diesel. Great
point. Yeah. And I think that's a really good point that Eric makes, and you'll pick up later as we talk about the spark-ignited low-pressure solutions. That is something that I'm not aware of any spark-ignited engine managing to achieve the same torque as diesel. So thanks for that one, Eric. Great. On this slide, there's a couple of key points I wanted to make, and just so I'm very clear, these are not the Scania engine on the right. This is actually a separate engine that we did run. But what the right-hand side shows is the ability for us to actually exceed the diesel power and torque. So as Eric noted on the previous one, we're matching up to their requirements on that diesel engine. In the engine that we have on the right here, it was actually running around 43% on natural gas, which is roughly in line with the diesel. But with the hydrogen, we were actually able to take that torque and that power level up by approximately 20 to 25%. So 3,000 Newton meters was achieved well within all the technical limits, and 600 horsepower on that particular engine. And again, as you just saw on the Scania engine, we were running 2,800 Newton meters. And again, also on these ones, the efficiency improvements are still there, even as we push the torque up. Now, on the left-hand slide, another important point to be aware of is that the hydrogen slip. So this would be the hydrogen that is potentially going to go down to the crankcase or is in contact with the piston and the cylinder walls, etc. Our hydrogen slip is essentially zero. We're basically burning all the hydrogen that's in the cylinder. That's important because it means that the engine doesn't have to worry about resident hydrogen. We don't have to worry about it in the crank. We don't have to worry about the components living in hydrogen within the engine. We have to worry just about the fuel injection system. So this is an area where the OEM has far less concern than on a typical engine where the hydrogen is resident for a period of time. So all very useful. I think there's one more graphic that pops up, and off we go. So one point I'll make as we go down, and some of the audience is probably aware of, but not everybody knows this, is brake thermal efficiency. That's a measure that we tend to use in the industry to really understand how efficient that engine is. So if you're looking at a typical spark-ignited engine, and you're going to see a little bit of this from Xander, the engines these days for spark ignition, in the old days of natural gas, were probably pushing 40%, maybe a little higher. We are seeing numbers into the 42, maybe 43% on spark-ignited systems. Achieving 51.5% is a whole new ballpark for them. That means that when your truck's on the road, you're going to see considerably better fuel economy than you will when you've got a spark-ignited engine. And that's really what's attracted people into the HPDI technology on natural gas so far, and we really expect that on hydrogen. And I know we're a bit tight on time, so a really quick look at the next generation where we're going, and then we'll dig into a couple more results and off we go. So in this particular case, what we're highlighting is that another innovation we mentioned in Vienna is our next generation fuel system. So earlier you'd seen a gas conditioning module on the left. we're replacing those with a couple of new components, which will enable us to beat both Euro 7 on natural gas, but more importantly, will enable hydrogen and higher pressures. So these two new components are really a key step forward for us. On the right-hand side, you'll notice that we show both a hydrogen off-engine system and an LNG system. On the vehicle itself, everything on the left will be standard, and on the right, we'll simply replace the storage system with hydrogen, and if not, with LNG, depending on the option required for the vehicle. That's the intent as we move toward that next gen. This is a quick overview of the system. This system has been shown previously with our current 2.0. The two components that we've replaced with are effectively superimposed just so you can see where they fit. But the really important part about them is they've allowed us to improve our gas pressure control, and in turn eliminate a small amount of dynamic venting, which previously we were tuning out with considerable calibration work. We're now able to solve that far more quickly and eliminate that. It also allows us to go to higher pressures, which will in the future with these new engines allow us to match them with either natural gas or hydrogen and keep up with the diesel efficiency. And then finally, some of you may be aware under the Euro 7 regulations, we now have onboard fuel consumption monitoring as a requirement. This is fully enables that part of the new legislation. Just a quick note that while some of you may have played with the ideal gas law to look at hydrogen storage, a key element here is that hydrogen doesn't believe fully according to ideal gas laws. So the message on this slide is simply that we need a fair bit of storage to get the appropriate amount of hydrogen on board. We're targeting about 80 kilograms on a typical vehicle, and that in turn is about 2,000 liters of storage. You're going to see a bit more on that as we go, but on our trucks, we figure we can get to approximately maximum of 600 kilometers without a compressor on board, just with the storage that's available on that truck. But we'd like to get more range. So one of the areas that we're working on, we're not going to tell you all the details yet. It's in the middle of our patenting process, but we've been looking at a smart tank system to allow us to increase the range while keeping our parasitics extremely low. With the trucks, we figure that a normal truck, we probably will be okay for up to about 500 kilometers. I'd noted 600 on the previous slide would be pushing it. The 500, we'd say, is about the cutoff point to want a compressor on board. The smart tank strategy is going to allow us to maximize that efficiency and minimize our compressor flow. And really, that's important around getting a smaller compressor, taking out the power requirement. We don't want to have too much parasitic, and keeping the weight down. I'm going to show you some of our simulated results, and Eric and I will probably share off each other a little bit on the following couple of slides. So, Eric, this is the Södertälje-Norrköping route. Maybe you can just give us a little bit of background on that.
It's a rather flat road with rather low consumption.
Yep. And on our simulation, Eric's provided us with the mapping for it. So this is just a simulation at this point. What we did was we took our compressor model, we put everything in place, and then we ran through what could we do while we're running that route. And what you'll see here is the fuel pressure is shown in green. That's an indication that the engine's receiving the pressure it needs. And you'll notice that just at the end of the route, above that 900 kilometer mark, we're starting to hit more on that fuel rail. But you'll also notice the engine power. And on this route, the power is approximately 300 kilowatts, about 400 horsepower at maximum loading. We're able to hit that throughout the cycle. So not just when we are at the early stage, but at the back end. And then you'll also notice a line is called compressor power, which is the blue one at the bottom. And what that shows is that for approximately the first 500 kilometers, we're really not touching on the compressor much. The way the strategy works, we will actually use a little bit of it early on. We effectively harvest some energy, if you like, or harvest some pressure. As we go further, though, we will use more of the compressor. But the interesting piece for us is over the entire cycle, our average power draw is approximately 2%. So we're really not taking down too much parasitic across the entire cycle. But to be fair, your first half of that cycle, you're really in your most efficient point. And then you'll just see the tank pressure reducing slowly down. If you measure against the left-hand or right-hand side, we bring that tank down to about 50 bar pressure with the compression system in place.
David,
So-
this has been verified by Scania's or Redon's own simulation tools.
Yes, yes. And that's a brilliant addition. It's not just our engineers looking at, but as Eric says, the Scania team has been looking very carefully because they have the same concerns. This one is multiple routes from the Scania team. And Eric, maybe you'd like to say a bit on this slide too, perhaps.
I'm unfortunately not very familiar with these routes, but I guess the description is true. The München road is a highway and rural. The Koblenz Trier is very hilly, and it is run with a Scandinavian vehicle load, which is 60 tons.
Yeah. I think that last is a very important point that Eric mentioned is typically on the loading, that's a very big, significant impact. So the previous slide, we'd shown a 20-ton load and almost 1,000 kilometers range. The 40-ton load, we're at about 600. We're really expecting that on a typical truck cycle, we're going to be around 800 kilometers of range, which, to be very honest with you, is the target that we started from, and which we're anticipating many people will be looking at about 800 kilometers on hydrogen. Fuel storage being what it is, the more storage you have on board, the further you go, of course, but a typical 80 kilograms of fuel will put you right into that sweet spot. Obviously, if we have a higher cycle or higher loading, which you see on the 60-ton, fuel economy does drop, but this is true of diesel as well. This is what happens when you have a heavy loaded truck and a hilly route. So I think this slide's going to be interesting. Yes.
I can add something there. And
Yes,
these
please.
driving ranges are achieved with a standard truck when it comes to wind resistance and rolling resistance. There is a very intensive work going on right now, primarily driven by the BEVs, which means that the wind resistance and the rolling resistance will be dramatically reduced in the future, in let's say 5 years from now, which means that these numbers will grow with 30%.
Yeah, that's a brilliant point. I think one last point I'll hit on, Eric, with any support from Xander in a little bit, is that the intriguing piece about the diesel cycle and why it's so important is that when you've got full power and full torque, these hilly ranges are well within the capability. When we look toward the spark ignited solutions, that's where the challenge becomes even higher, is because their torque profiles are so much more challenged. Your fuel efficiency drops quite a bit. We've seen with the natural gas trucks that while in standard use on a road cycle, the SI engine lags by perhaps 20%, depending on the exact cycle. It can actually be worse when we've got hilly ranges, etc. So that power and torque we mentioned earlier is really important as you get up into these heavily loaded trucks. I know time is short. Let's move down to the last couple of slides, and it gives Xander a chance as well. So I'm going to talk very quickly on our demonstration trucks. Like I mentioned earlier, on the left, we kept the exact same current hardware, gas conditioning module. We simply swapped out the LNG system and put on the hydrogen storage you see on the right. On this slide, I'll just talk very quickly about a few challenges on our demonstration trucks. We have 2 trucks currently. One of those trucks is in the US and one is in Europe. But some of the challenges currently in the world we live in is really getting permits for these trucks. So not everybody's ready for hydrogen trucks quite yet. We're a little ahead of the curve, in fact. And then fueling them. In many locations, and I can use the US as an example here, we have been up to 1,300 kilometers away from the nearest hydrogen station. So while we're getting ourselves ready, the infrastructure is moving in parallel. And of course, we expect that as time passes, all of these will meet up appropriately. But right now, it has been somewhat of a challenge to get fuel available and to get the trucks legally allowed on certain roads. Once they're there, though, we've been able to run these trucks. The video that we didn't, that we just skipped past a minute ago, actually does demonstrate our hydrogen demonstration truck on a highway pulling a load down in the US. Now, the next couple of stages, we will be adding some more fuel to that truck. Sorry, our slides just reversed there. My apologies for that. So the next while we will be increasing the fuel storage on our trucks so that we can get more range. And obviously, as the permitting solves, we want to be demonstrating how we can pull loads with it. And then we'll be adding our fuel compressor a little bit later once we've got a little bit more of the testing out of the way. Right now, it's all about demonstration at this stage. Maybe just a quick summary. Kept the same fuel system architecture, whether it's methane or hydrogen, just swapped out the diesel system. We've got multiple projects underway, but the Scania one we're highlighting here is one with one of the most efficient engines the world has seen, 51.5%. We've already got to near zero CO2. And as we head toward our new fuel system, we're really looking for major improvements as we meet the next generation Euro 7 regulations. And finally, we've got a demonstration truck on the road. You just saw a picture of it, and hopefully you can see the video on our site. But it's here, it's now, we're able to run. I think that covers me off. The next one up will be Xander.
Yes, thank you, David. Looking at time, I will quickly take over, presenting an overview of the TNO paper we presented at Vienna, end of April, presenting results, experimental results from our single cylinder setup, as you can see here in the picture. What we targeted with our paper was to make a fair comparison between two different combustion concepts for the hydrogen internal combustion engine, being the lean burn spark ignited concept with port fuel injection, so hydrogen injection into the intake manifold, and Westport's HPDI concept. We targeted a fair comparison, and we did that by also comparing these two concepts using one and the same base single cylinder heavy duty research engine, and then considering key performance indicators like power density, efficiency, and engine out NOx emissions. If you look into literature, such a comparison, the two concepts on one and the same platform, that's quite unique. So we were also with pride presenting these results. So I will very briefly discuss some results on our setup, then a quick overview of the PSI results and some details on the HPDI combustion characteristics that we identified within our setup, and then focus on the comparison between the two concepts and ending with some summarizing conclusions. So here, some details on the setup. In the middle, the architecture of the setup is shown. The base engine is actually a diesel engine, and our single cylinder engine has a sweat volume of 1.8 liters. In our setup, the engine is fed with air by using an external compressor, so there's no turbocharger, which also decouples the fuel part from the air part and provides great flexibility in setting different operating and load conditions. Although we have an EGR system equipped on the setup, the measurements I will present today did not make use of EGR, so all measurements are run without EGR. And important to note that our setup had a maximum in-cylinder pressure, a limit of 230 bars. On the left-hand side, you see the PFI-SI concept visualized, where the hydrogen is injected into the intake runner of the engine. And what is good to note here is that the base engine was a diesel engine, so we had to design a new piston to accommodate the PFI-SI concept, a bathtub type piston ball geometry, and a compression ratio of 12.5, which is significantly lower than the base diesel engine. And in our setup, we could vary the compression ratio between 10 and 12.5. On the right-hand side, we see the HPDI concept, where both hydrogen and the pilot fuel are directly injected with pressures up to 350 bar in our case. And we used a roughly 3% energy share from the pilot fuel throughout our measurements, being about 6 milligrams of pilot fuel. For HPDI, we could make a direct use of the base diesel piston with a compression ratio of 18.5. So no new design required there. In our measurements, we focused on an engine speed of 1500 RPM, which is not a typical automotive speed, but is a engine speed that is quite typical for fixed speed power generation applications, gensets. And that's basically also an artifact from our research on PFI-SI, which targets also stationary power generation as an application. And to make then a fair comparison, we also ran the HPDI concept at this 1500 RPM. So first, a brief overview of the PFI-SI results. Here, the graph summarizes the obtained NOx emissions as a function of the load in BMAP, and also it shows in blue the required intake manifold pressure, the boost pressure. What can be clearly seen is that the PFI-SI concept has good potential to realize extremely low engine out NOx, up to a load of about 17 bar BMAP. NOx, engine out NOx emissions were well below 0.2 grams per kilowatt hour, that you can achieve by running the engine in a very lean mode, so with lambdas of 2.5 up to 3 and even higher, requiring also quite a high boost pressure, as you can see by the blue dots in the figure. And at maximum loads we could obtain, also the boost pressure is close to 4 bars absolute and close to the maximum achievable pressure in our setup. At maximum load, the operating point for this low NOx is also limited next to the available boost pressure also by the occurrence of knock, which is a combustion instability where the incident charge ignites before actually the spark plug is actuated. So that results in unstable combustion. We try to shift the knock limit and extend the operating range by also lowering the compression ratio of the engine. So going from 12.5 down to 10 allowed us to extend the load range up to 21 bar BMAP. However, with an additional increase in engine out NOx to above 4 grams per kilowatt hour, and also with a reduction in efficiency. So at the compression ratio of 12, we were close to 44% net indicated efficiency. And at the compression ratio of 10, that reduces to 42.7%. We were able to realize quite a decent load of 21 bar BMAP in the setup. In an attempt to further extend the load range, we also applied the injection of water to the intake manifold. Injecting water and a subsequent evaporation of water cools down the incident charge, also reducing the tendency towards knock, so unstable combustion, which allowed us to increase the fueling, reducing lambda and extending the load range up to 24 bars of BMAP. However, again, at the expense of increased engine out NOx to about 7 grams per kilowatt hour, still with quite a decent efficiency of 43% net indicated. This presents an overview of the PFI-SI concept and the results we obtained there. Low NOx potential, also quite significant load that could be realized, but not at the same time. And also high loads requiring quite non-standard systems like water injection and a significant reduction of the compression ratio. So next we move to the HPDI. We used our setup to identify some key combustion characteristics of the HPDI process, quantifying efficiency, power density, and engine out NOx. And we applied several variations on pilot fuel injection timing relative to the main. Injection pressure has been varied, intake manifold boost pressure, so lambda has been varied, and also we varied the hydrogen injection timing. Also at the same load points as we did for the PFI-SI engine in order to make a comparison between the two concepts. So here a more deep dive into the actual combustion, showing here results for a variation in pilot fuel injection timing relative to the hydrogen main injection timing. So at the top you see the current profiles for the diesel pilot, current profiles to the HPDI injector, and in the middle the current profile, activation profile to the HPDI injector for the hydrogen injection. And at the bottom, you see the heat released from the combustion process. So the heat release profile and the resulting incident pressure curve. What you can clearly see is that when you shift the pilot injection timing, clearly see that the heat release from the pilot also changes. It shifts and it changes somewhat in shape as well. But if you look at the main heat release from the hydrogen, it's almost invariant to the phasing of the pilot fuel, which also means that if we look at factors that determine the efficiency, it's mostly the hydrogen injection timing and the phasing that results from that determines efficiency. So also from control point of view, that makes life a bit more easy. And what these results show is it also hints at potential for reducing the pilot fuel quantity. As said, we were now at 6 milligrams per injection. If the pilot increases the temperature up to a certain level, then the hydrogen is able to ignite. Any further increase in temperature doesn't result in an earlier ignition of the hydrogen. So which also hints at that this pilot fuel quantity is actually on the large side and that a reduction is very well possible. That's also what we try to analyze next in our research. We also varied the injection pressure, increasing it from 250 bar up to 310, while keeping the combustion phasing fixed at about 8 crank angle degrees after top dead center. So what you can see from the heat release profiles is that the burning rate increases significantly with increased injection pressures. It's a mixing control process driven by the injector momentum, fuel injection pressure. However, at fixed combustion phasing, if you look at the table, then we see that actually the efficiencies and also engine out NOx values are very close together for all three levels of injection pressure, where the indicated thermal efficiency is all around 51.34%, so very close together. And engine out NOx at this efficiency is close to 16-17 grams per kilowatt hour. So this also showed there that there is potential for reducing injection pressures without a significant loss in efficiency, and also with a very limited impact on engine out NOx. And lower injection pressure also might be beneficial to increase the range. You can rely on more hydrogen from your storage tank. We also varied the boost pressure, so the intake manifold pressure, which is equivalent to changing the air-fuel ratio, lambda, increasing the boost pressure from 160 to 180 to 210 kilopascal relative to ambient, resulting in lambda variation from 2.2 and 2.6. And here the efficiency and the NOx emissions are shown for these different boost pressures and a variation in the hydrogen injection timing. So combustion changes, combustion phasing varies. What you can see in the upper left figure showing the net indicated thermal efficiency is that for all boost pressures, the efficiency curves are very close together, and they max out at about 51.5%. Also indicating that there's a limited impact of the boost pressure on this efficiency. However, if we look at the figure on the right, showing the NOx emissions for the different boost pressures and for different combustion phasings, we do see that at these maximum efficiency, so combustion phasing, let's say at 6 to 8 crank angle degrees after top dead center, engine out NOx emissions are actually relatively high. So here, when going to a more acceptable typical diesel-like range of, let's say, 10, 12, 14 grams per kilowatt hour, then we must delay the combustion slightly to, let's say, 10 to 12 crank angles after top dead center in order to get in this acceptable NOx window. But still, if you then look at the efficiencies that we obtain, these efficiencies are still quite high and still very competitive to the conventional compression ignition or diesel engines. So they are still around 50%. So high efficiency above 50% is possible at the engine out NOx levels well within the diesel range and very much competitive to diesel. So similar to the PFI SI concept, we also ran the 24-bar BMAP low point at 1500 RPM. The hydrogen injection timing sweep is shown here in red, 16-bar BMAP low point in blue as reference. What these results show is that PFI SI, we needed very high boost pressures, water injection to realize this 24 bars of BMAP. Within the HPDI concept, we could use conventional boost pressures here in the range of 160 and 210 kPa relative to ambient pressure. So that is very conventional values that are found here, quite easily realizing the 24 bar of BMAP load. However, what you see here is that the setup was becoming limiting in obtaining and realizing the full efficiency potential. As you can see here in red at the top left figure, we could not advance combustion phasing before 10 crank angle degrees after top dead center without crossing the maximum incident pressure limit, which is shown in the figure below, of 230 bars. So here we could not realize the full efficiency potential. However, again, looking at the NOx emissions, it's also in order to remain within an acceptable range, as similar to diesel, 10 to 14 grams per kilowatt hours engine out NOx, found combustion phasings at this slightly more retarded timing also realize these engine out NOx levels that are within 10 to 14 grams per kilowatt hour. So at this 24 bar BMAP, we achieve diesel-like NOx levels and also with efficiencies that are competitive to diesel engine efficiency. These results also show that although the efficiency potential could not be fully realized due to the incident pressure limit, it is such that any development in after treatment will also be beneficial for realizing the full efficiency potential that is actually there, because that will allow higher engine out NOx and going more towards higher efficiencies. And of course, increasing of the incident pressure constraints will also help in realizing higher efficiencies well above typical diesel range. So now for the comparison, here for at 1500 RPM, the PFI SI results on net indicated efficiency are shown in blue for 16 bar BMAP and the 24 bar BMAP, including water injection, are shown here in blue, and HPDI results for at 16 bar BMAP and 24 bar BMAP are shown in red. It's clearly visible that regarding efficiency, HPDI clearly outperforms the PFI SI concept with about 7 to 8% point higher efficiency for HPDI than was found for PFI SI. Even if we account for retarded combustion phasing required to get within a more acceptable engine out NOx range, the HPDI concept still has a 6 or 7% point higher efficiency than PFI SI. HPDI clearly outperforms the PFI concept there regarding efficiency. It's not well visible, but in the comparison here, the top right figure shows the NOx emissions. In blue again, PFI SI, in red the HPDI, and here you can clearly see that regarding engine out NOx, the PFI SI concept has the potential for extremely low engine out NOx, where HPDI has more diesel-like engine out NOx. So regarding engine out NOx and potential to reduce after treatment, there the PFI SI concept has a higher potential. But again, in order to combine that with a high load, we needed quite non-conventional systems like water injection and a very high boost pressure for the PFI system to realize, let's say, 24 bar BMAP. So well within the diesel range, while for HPDI, conventional boost pressure levels could be used, and this 24 bar BMAP was realized quite easily. Now that we know efficiencies and engine out NOx values, we can also take a look at the CO2 footprint of these two different concepts, starting with the electricity mix in the EU at present being 250 grams per kilowatt hour. In order to get the hydrogen into the storage tank of the vehicle, we first need to produce it using an electrolyzer with the use of this electricity mix and an typical electrolyzer efficiencies of 65%. A CO2 footprint for hydrogen production of 285 grams per kilowatt hour results. Then transporting it and compressing it such that it can be fueled into the vehicle. Efficiency there taken of 87% results in a well-to-tank efficiency. So the hydrogen in your vehicle of 442 grams per kilowatt hour for both concepts. Then we assume that the hydrogen flow, the required hydrogen flow, is the same for both concepts, but in reality they will differ because also the efficiency of the engine greatly differs. So here we have taken an 8% point higher efficiency for HPDI, which we also found in our measurements, which result in a well-to-tank CO2 footprint in grams per kilowatt hour on engine brake level, which is significantly lower for HPDI, resulting from this higher efficiency. If we want to go then for full well-to-wheel CO2 footprint, we also need to consider the additional CO2 share resulting from the pilot fuel and also the somewhat higher consumption of AdBlue, which could also result in CO2, which are higher for HPDI. But even if we take that into account, and then you're talking about a tank-to-wheel CO2, additional CO2 of about 25 grams per kilowatt hour for HPDI and 1-ish for PFI SI. But then still, the well-to-wheel CO2 footprint of HPDI is significantly lower than for PFI SI. with 944 grams per kilowatt hour against 1107 grams per kilowatt hour, purely because the HPDI engine is superior on efficiency. Now, if we extrapolate this analysis towards the future, let's say the 2040 timeframe, we can assume a lower CO2 footprint from the EU electricity mix. So it's going down to 60 grams per kilowatt hour. Electrolyzer efficiency increases, transport losses reduce, but then still engine efficiencies increase, but still with an 8% difference. Then still looking at the well-to-wheel CO2 footprints, although the values are coming a bit closer together, but here still HPDI has a lower CO2 footprint than the SI concept. So this also shows the importance of not only looking at tailpipe CO2, but more with a broader view, looking at complete well-to-wheel CO2 footprint. You see that HPDI, the higher efficiency of HPDI results in a lower CO2 footprint, which is also valid for the longer term. Also, within the 2040 timeframe, HPDI still has a lower CO2 footprint than the PFI-SI concept. So contributing to decarbonizing society, also HPDI is a very good technology for this, even with the use of a pilot fuel that contains carbon. So then some summarizing conclusions. So we made this comparison between PFI-SI using one and the same base single cylinder research setup. Regarding efficiency, HPDI clearly outperforming the PFI-SI concept, even taking into account somewhat retarded combustion phasing for lower engine out NOx. Still a 6 to 7% point higher efficiency is found for HPDI than for PFI-SI. Engine out NOx, PFI-SI has a clear low NOx potential for medium to medium high load, where HPDI has more diesel-like engine out NOx, but still with very competitive efficiencies, exceeding conventional compression ignition engines. For power densities, both concepts could realize 24 bar BMAP within diesel range, I would say. However, for the PFI-SI concept, we needed to use very high boost pressures and also the use of water injection, so significantly adding complexity to the system. While for HPDI, we could realize this 24 bar BMAP with conventional charging, also with the base diesel engine piston, and there's even potential for higher power density when the maximum allowable in-cylinder pressure of the setup would be increased. Regarding CO2 footprint, considering current EU electricity mix, HPDI has a lower well-to-tank and well-to-wheel CO2 footprint than the PFI engine, also on the longer term, going towards 2040 timeframe. So I think that was my last slide. I was happy to answer any of the questions.
Awesome. Thank you so much. And I know we have certainly gone way over time. There was tons of material for you guys to cover, so I really appreciate it. And recognizing that we are way over time, I'm only going to ask a couple of the questions, but I do commit to anybody who has submitted one. I will work with this group of panelists and get answers for you as soon as possible. But the first question that we had pop up was for you, Xander, and it says, are you also planning or have you already performed measurement on a multi-cylinder engine?
For the PFI-SI concept, we are within a nationally funded project where we have a PFI-SI concept in development for a stationary power genset. So there we have run also a multi-cylinder engine, also showing low engine out NOx, but with a load range that is, let's say, just touching the lowest power range of diesel. For HPDI concept, the next step is to implement the HPDI concept also on a larger in-cylinder, single-cylinder engine towards a maritime application. And ultimately, we are also targeting in a follow-up project to implement the HPDI system on a multi-cylinder engine, but also there currently also towards a bigger engine for maritime operation.
This one is for Fabien and or David, I guess. Can you provide a bit more detail on the smart tank system? What are the limitations of currently available systems that make Westport want to pursue the smart tank option, and what is the anticipated benefit or uplift?
So the smart tank system, as I noted in the presentation, there's a bit of patenting going on around it, so I'll be a little cautious on what I say, as there are some very novel ideas that we are incorporating. At the same time, as you noted, why would we pursue it? What are others doing? there is not a lot of onboard compression technology available, period, even for mobile solutions, that is, or even natural gas. But as we looked at it, we had a few ideas that we thought would come from, and some of them echo where you are already on stationary compressors, but the mobile applications require a whole different bit of technology development around vibration and just the vehicle environment. So as we looked at it, we also realized most compressors are quite large. We've been focused on bringing that compression size down much smaller and about optimizing it to the way the vehicle runs so that we can both work with the package available, but ensure that we have the maximum possible efficiency and the minimum possible parasitic. Those two go together across the full range of the vehicle's operation. So it became a no-brainer. We're really good on cryogenics. We're really good on off-engine systems. We've got a lot of controls experience. We put that together with the fact that we've done in the past a few compressors, married it, and right now we're happily moving forward toward a really good solution for on-road trucking.
In your view, is the growth for this technology primarily anticipated to be a result of a pull from customers, or is the growth going to be driven by a regulatory push?
I think it's both. We see a great interest in hydrogen from our customers, and we don't believe that we will be able to sell enough BEV vehicles to comply with the 45% reduction in 2030. So we need hydrogen vehicles also.
What we are seeing, thank you, Eric, for your comments. Certainly, what we are seeing from the marketplace, and so our customers, Westport Fuel Systems, is tier one. Our customers are the truck OEMs. We are seeing very significant growth in interest for hydrogen technologies in general. And I think not only the final customers, but the OEMs are really finding that there is a very important role for hydrogen combustion to play to complement some of the hydrogen fuel cell and battery electric vehicles to ultimately meet in the highest volume and reduce CO2 in the most efficient way. I think that's a solution that not only customers, but also the regulators are starting to see. Like I mentioned earlier, some of the regulatory solutions that are being proposed are enabling more and more combustion ICE engines to part of the solution.
I think those are valuable points, Fabien. I'd also note that we're seeing interest across much of the larger engine sector from the customer base, not just in heavy duty trucking, but out beyond that into the maritime or marine, rail, etc. industries, because legislation helps shape the picture of the world we're in and puts the boundaries on it. But many of them are looking for that efficient solution. And when we get into the off-road sector, that's another area where they're searching for solutions, and how you decarbonize those large engines is quite difficult. This technology really opens up in that they are so reliant on the power and torque of their engines, and the efficiency gain is important because fuel is at the end of it. That's where your economics lie.
Awesome. Thank you, David. And thank you everyone for joining. I really appreciate Eric, Fabien, David, and Xander joining and taking time out of their already busy schedules to walk us through this. I know we have some more outstanding Q&As. I will make sure that I get answers to those that submitted them. And if anyone has anything pop up, fire me an email and I'll get some answers to you as well. Enjoy the rest of your day. Thank you, everyone.
Thank you.
Thank you.
Bye.
Bye-bye.